laser pointer here. So hopefully you can see that and everything's okay. So yeah, so today I'm going to tell you about some of the recent work we've been doing in terms of quantum photonics. We do a lot of work in quantum and nonlinear photonics, and in fact, right there you can see this is a chip. It's a photonic chip that's based on silicon nitride, but we certainly we're open to doing non-chip based nonlinear photonics. But what I'll tell you about is something that really is a potential way of thinking about quantum domain processing that's hopefully different from what maybe a number of you have thought about. So, kind of the most basic, when I took, when I was at Rochester as a grad student, I took a quantum optics course from Len Mandel, who is really one of the original people that did many of the most important experiments in quantum optics that you can think of. And certainly when he used to draw this simple picture, and he was a fantastic lecturer, by the way, really, as brilliant as he was also just a great professor. And the notes you took from his class, I still go back to them. They're really good. So here's kind of one of the simplest ways of thinking about a quantum phenomenon, which is entanglement, which arguably is the most important aspect of quantum optics and quantum photonics. And it consists of a single photon striking a beam splitter. And assume this beam splitter is a 50-50 beam splitter. So there's a 50-50 chance of the photon going up this way or going to the right. And if you're to write the state of the system after the photon strikes this beam splitter, you can think of it as being, there's a probability of being in one arm and not in the other, or vice versa. And so when you write this state, you can write it out in this sort of linear superposition that can't be decomposed in any trivial way. And so this is called an entangled state. It's the simplest way of generating entangled states. And of course, there's a lot of interest in this was the original version, and now there's more higher dimensional versions of this, and certainly for quantum computing, this is one of the real hearts of it. So what I'd like to do, and I know this is maybe jumping ahead, but it's kind of to tell you what is the basis for everything I'll be talking about for the rest of this talk, which is to think about this kind of entanglement, which I just told you about in the spatial domain. But now the idea is to think about is it doesn't have to be in the spatial domain, and probably many of you have even thought about doing entanglement. There's time domain as well. And here, what I'm going to be telling you about today is a type of entanglement that can occur in the frequency domain. And it has everything is completely analogous to what you might think of in terms of spatial domain. And what it all boils down to is creating a beam splitter, just like I showed you there, but in the frequency domain. And so here I've drawn the beam splitter that we'll be studying here. It's based on a parametric nonlinear process called four-wave mixing. And so you have a third-order nonlinear medium, and we choose to use a third-order nonlinear medium because a lot of nonlinear photonics, like silicon nitride, silicon, all have chi3 but don't have chi2. And so we're going to focus on chi3 here. And what you do is you take two pump waves and you inject them into your chi3 medium. And it turns out that forms a beam splitter in the frequency domain. Okay, so the idea is if I now come in with, let's say, a single photon, what you'll find is if you adjust the powers, for example, of these pump waves, such that they're just the right power, there is a 50-50 chance of the photon staying in the color that it's in, or converting to a new color, let's say a green color. And it turns out if you write the state of the system for the photon now, this is in the frequency domain, where the photon might be green, 50% chance it's green, or blue, 50% blue. And it turns out that the state of the system looks just like that of a beam splitter. And if you want to think in terms of the photon interaction, in terms of the four-wave mixing process, it's in the top right here, is I'm annihilating a red photon, annihilating this signal photon, or here, the blue one. And then I'm creating a kind of yellow photon, omega-1, and a green photon, omega-3. And if these two omega-4 and omega-1 photons are really strong, as I've shown them here, then you have this beam splitter relationship between omega-2 and omega-3. So that's where it comes from. Okay, and so this is the process that we're going to be using. using for the rest of my talk is all based on this. And we've been able, in my group, we've been able to do this with very high efficiencies. So we can now routinely get efficiencies of 97% conversion from, let's say, blue to green. And of course, if we then scale back the efficiency, we can operate in this 50% conversion regime, which is just like this beam splitter that I'm showing you here. Okay. So just to see where kind of this technology has been going, and again, the big interest for a lot of these quantum applications is building a quantum computer. And of course, certainly there's been a lot of work, and certainly a lot of work being done at Calgary, University of Calgary, on various aspects. But one of them, of course, is using superconducting qubits, but there's also a big push trying to do this in photonics. And so, for example, Jeremy O'Brien with Mark Thompson at Bristol, they started a company called Psi Computing. Actually, one of my former students and postdocs is working there. And they wanted to use photonics to build a quantum computer. And this was a paper that was just published a couple of years ago, which was kind of showing at least the beginnings of how you might build such a quantum computer. And it consists of, taking a pump wave coming in, splitting this pump wave into many different components, and then going into these spiral waveguides here. And these spiral waveguides were going to generate photon pairs. And so these photon pairs are actually generated here. And that's a different type of forward mixing. So that's different from the one that I'll be talking about for most of my talk. It consists of just a single pump wave, not two, but you come in and you generate correlated photon pairs in this way. Okay, and here you're annihilating two pump photons, creating a signal idler. They're strongly correlated. And you could write down, for example, the field for this equation here. It obeys kind of this simple coupling between the idler and the signal. But this behaves more like an amplifier. It's a parametric amplifier. And so even in the absence of any input signal or idler, you generate these photons, but they're strongly correlated. You detect one of them and you've heralded this red photon here. And this is how you can generate these photon pairs. So if we go back to here, they're generating their photon pairs here. Then they're kind of separating them out and routing them. So you have all these blue ones and red ones here. And then you do these beams, you entangle them. So this is using what I mentioned at the beginning of the talk. This is higher order entanglement. It's not, one of these would correspond to what I showed you, but now they want multiple of these. And the idea is, if you can get all these photons lined up at one time, you can do this higher order dimensional entanglement, which is necessary for building this quantum computer. But here's a key aspect here. Is, to make this useful, you probably need thousands, if not millions of photons being generated. And so you can see here, I'm probably only generating, I don't know, maybe of the order of 15 to 20. And if you want to get up there, that means that I have to scale the circuit, the photonic circuit, up to very large amounts. I mean, it's got to be pretty huge. And if you look at least current losses in many of these silicon, this was a silicon-based device. If you look at the losses here, scaling up is very challenging because the losses are so high in silicon. You can only go maybe a centimeter, maybe a couple centimeters at best before losses start killing you. And as we know, in any quantum device, losses must be avoided at all costs. So again, what I want to try to sell and get you thinking about is if we can build these frequency beam splitters and develop processing that can occur in the frequency domain, the nice thing about it is you don't have to scale up your circuit in terms of size to add higher dimensions. What you need to do, as I'll show you, is add more pump fields. But your interaction inside your medium can be the same. All we're going to be doing is adding more pump fields. And in that way, you can scale more quantum fields, add more photons in a way that doesn't scale with size. And so this allows you, and this is a key aspect of why we're interested in pursuing frequency domain quantum photonics, is the scaling on loss is much more favorable than it is in the time domain or in spatial domain. And so this is an important key feature here. And so much of what we're doing is just the beginnings of trying to think about frequency domain quantum photonics. So there's actually been quite a bit of work over the last few years looking at frequency domain quantum photonics. And this includes work that I'll be telling you about today, which are these three different aspects, which is Ramsey interference, frequency domain Hong-Ou-Mandel interference, frequency multiplexing to try to generate a near deterministic photon source. But there's certainly been Chi2 versions of frequency domain and also higher order frequency domain, time frequency domain entanglement from other groups as well. But what I'll be focusing on today is telling you a little bit about these three. I'll be adding a little bits and pieces of other things here, but these are going to be the main parts of my talk here and what I'll be focusing on. So this frequency domain processing, as I just mentioned is really requires what's called quantum frequency conversion. And actually, when people think about quantum frequency conversion, they don't think about operating in the 50% conversion regime. What people want to do is they want to take some quantum state, which could be a single photon, for example, that's maybe blue, and convert its frequency with very high efficiency, extremely low noise to a new frequency that's green, for example. And you want to be able to do this with incredibly high efficiency, 100% or as close to it as you can get. And you want to do it with very low noise. And because of course, the key part is you want to preserve the fidelity of the quantum state. That is, if I put in a single photon state here, I want it to be single photon, but maybe I have a more complicated state. And the application, much of it, which has been, and I'm sure, many of your groups, including Paul's group and others groups at Calgary are thinking about this, which is, a lot of the quantum memories, diamond NV centers that a lot of work's being done at Calgary are interested in this. But those are all, in the regime of 600 to 700 nanometers. But of course, if you want to take those quantum states and convert them to send them somewhere else, you want to convert them to 1550. And so, of course, you would like to be able to, seamlessly change that quantum state or that photon that you've stored there to 1550, and then go back from 1550 back to that quantum state so you can interact maybe with two diamond NV centers that could be kilometers apart. Of course, an extreme version of this, which, sometimes this is called quantum transduction, but it's really quantum frequency conversion, and that's interfacing from the microwave to telecom regime. So that's another, version of quantum frequency conversion. It's actually something that my group's thinking about. And then, of course, actually, there's a long history of this. People even trying to do astronomy, trying to detect things that are very far deep in space in the mid-infrared where there aren't good quantum detectors. What they were thinking about was converting those photons to, in the mid-infrared or maybe deeper, into visible or near infrared where there are really good single photon detectors. So quantum frequency conversion has a long history, and certainly there's a lot of interest. But what I want you thinking about today is, if you can build a quantum frequency converter that gets close to 100%, then you can also think in a completely different regime, which is thinking about 50% conversion. And then when you operate in the 50%, you have a unitary transformation, as this is, but now one that can generate entangled states. So again, there's a long history in nonlinear photonics of thinking about this single frequency photon translation. And, I think the first early paper on this was done by Prem Kumar, thinking about an optics letters paper, thinking about Chi2 frequency translation, and certainly demonstration of this in Piplin. But there's also been a lot of work done on Chi3, and a lot of the early work on Chi3 suffered from either poor conversion efficiencies or high noise. And so what I'll be telling you about today is work in which we've been able to do both very high conversion efficiencies. I think the highest conversion efficiencies have been demonstrated by anyone, approaching 97%, and low noise simultaneously. Okay. So as I mentioned, the first version by Prem Kumar's group was doing Chi2. And so, the idea is you had some nonlinear medium here. You have a signal. It's going to interact with a pump wave. And if you want to think in terms of this photon picture here, I have my signal here, which, is a few photons. I have a strong classical pump wave. And again, if you look at the relationship between the Idler field and the signal field here, the converted field, it obeys this beam splitter unitary transformation. That is the Idler's cosine times itself plus a sine times a signal. And so if you can make, and this theta here, this nonlinear here, just depends on the power of your pump wave. And so if you operate in the regime where theta nonlinear is pi over 2, then this vanishes. And now you have complete conversion of the Idler to the signal, and it's behaving like your ideal quantum frequency converter. However, for the applications we're interested, which is the beam splitter version, you want theta nonlinear to be pi over 4. And then under these conditions, this becomes 1 over square root of 2, and then it looks just like a beam splitter, 50-50 beam splitter. So as I mentioned, we're going to use 4-wave mixing to study this. And so instead of one pump wave, and let me back up. So you'd say, well, why not just do the chi2? Well, one key part here is a signal and idler are very different wavelengths. And this raises a number of challenges. It certainly can be done, and a number of groups are working this and shown impressive results. But it means, particularly if you want to go into use integrated photonics, is I need to overlap and have, signal and idler, which can differ by roughly a factor of 2 in terms of their frequencies. It can be challenging to get them to have, couple all these waves into an integrated photonic structure. So we're motivated to use chi3, where all the wavelengths can be comparable, or at least in this, similar. And it turns out if you work through all the math, you get exactly the same unitary transformation for the idler field as with a signal field as you do in the chi2 case. So it's exactly the same. And again, the advantage is all materials have chi3, including many integrated photonics materials. The wavelengths can be always similar. And again, if you want to scale this up so that you're dealing with millions of components, in principle, this could scale up to, this in a CMOS scalable platform where you have photonics, electronics all mixed in together. Another subtle part, and I won't go too much in this detail, but typically what you find is that the phase matching, that is the condition in which you satisfy momentum conservation for this nonlinear process, it can be made very broadband in the chi3 case, I think a little more easily than you could in the chi2 case. And so that's another subtle advantage, but it can be an important one, particularly if you're trying to scale to many wavelengths. So as I mentioned, so here's this magical chi3 process, which is producing this frequency conversion. So I wanted to give you kind of a classical description of what's actually going on here. So imagine you have your medium here, which has a chi3. And another way of thinking about it is when I have a chi3, that's the same as saying that the index of refraction of the material is intensity dependent. So N scales with the intensity of the material. So imagine now I have 2 pump waves at different frequencies. So what that means is those 2 pump waves will interfere. And so in interfering, you'll actually form a grating inside the material, a traveling grating, because they're at different frequencies, which will travel through the material. And of course, the spacing of that grating depends on the frequency difference here. If I come in with a signal field, it sees this grating, this index grating, and it scatters off that index grating. It's like a Bragg grating here, and it'll generate an idler field. Okay, so depending on the frequency difference, which way this grating is moving, it'll create an idler field which can be upshifted or downshifted from the signal. And so this is classically what's going on. It's almost, if you want to think in terms of an acousto-optic modulator, it's just that this is not an acoustic wave, it's actually a photonic index grating that's actually created inside that material. But if you look at the nonlinear strength, which depends on the powers of these 2 pump waves, and you can see that the signal wave, as it propagates through the material, or as a function of this nonlinear strength, it goes down. And when you get into this regime of pi over 2, then it completely has converted all its radiation to this idler wave. So this is the classical description of this process. So as I mentioned, there's this subtle part, what's called phase matching, which is, of course, here as I've drawn it, all the energies add up together. But if you want this process to occur efficiently throughout the entire medium, you also have to have all the wave vectors add up as well. And so that means that, K1, this pump, Ks of the signal, have to add up to K2 of this other pump, and Ki of the pump of the signal. And this is non-trivial because the refractive index is inside these propagation constants. And that means you have the refractive index. And the refractive index changes with frequency. There's dispersion. And so as a result, it turns out if you work through all the math, and we're not going to do that here, but it turns out that the condition in order to achieve that phase matching, here's one configuration that works. If your 2 pumps, if your signal and idler are on this wave here, the 2 pump waves are at this different location here. And it turns out the frequency separation of the signal and idler are equal to just have to be equal to the separation of the two pump waves, okay? And it turns out what you need is at the zero group velocity dispersion, the point at which zero group velocity dispersion has to sit right in between the average of these two. And if you, so I have some group velocity dispersion, it goes through zero. And at that point, I just make sure my signal and idler and my two pumps are symmetrically on either side. And under those conditions, delta K goes to zero. So we have Chi3 platforms in which we can do this. So everything I'll be telling you about today, we do in fiber. But currently, we're working very hard on doing this in an integrated structure, which is silicon nitride is what we're focusing on. And again, fiber is great, but you do have to overcome Raman. Not only that, is the lengths we'll be working with are like 100 meters, so it's a lot of fiber. And so we prefer to do this all in an integrated structure, and that's what we're working on. And a big advantage of using these is we can avoid Raman noise that is always a problem inside fibers. So as I mentioned, we have all these sources of noise. So this is the configuration that we're working on. We have two pump waves that are kind of in the telecom band. And then what we do is we put the signal and idler at shorter wavelengths, and they are all the way down here at 1200. So why do we do that? Well, one is, if you remember earlier, when you take a single pump wave and you put it inside a material, you generate correlated photons. And that's indicated here by this kind of purplish part here. So they're generating photons due to this other four-wave mixing process, and we want to avoid it. So that's why we keep this separation very large. Okay. So that's one aspect. The other one is that we have Raman scattering. And if you have these pump waves, then it means that on the long wavelength side, we have gain for those Raman. So there's a lot of Raman photons there. Now you have less Raman photons because you're on what's called the anti-Stokes side, but they're still indicated by the red line. Even at room temperature, there's still quite a lot. And so what we do to eliminate that is to actually cool the fiber. So the fiber is actually put in a dewar of liquid nitrogen. And it turns out if you look at the anti-Stokes Raman, it actually dies off, pretty rapidly. And so by operating here, we've completely eliminated any effects of Raman. And so much of the early work that was done with photons, with Raman scattering, it was a real problem. And so by doing this, by cooling the fiber, we eliminate that. So here's an experiment that we did. So this was a kind of the very first experiment. We generated single photons using a Chi2 pipelin, and then we interacted with two pump waves here, and we had a highly nonlinear fiber where they interact, and then we detect the idler, and we try to look at its properties and look at its conversion as we change the intensity of the pump waves. So here what you can see is at room temperature, if we and the pumps are pulsed, they're about 2 nanoseconds. So this is kind of in the two nanosecond region is kind of would be this region. And what you see here is that, over this window, we generate a lot of noise photons, and that's due to the Raman, the anti-Stokes Raman photons. But if we cool the fiber, you can see that basically it goes down to almost zero, so that the probability of actually generating a Raman generated photon within a window of our pulse is, much less than a fraction of a percent. And so with this way, we've completely eliminated that. And so this was early work we've done where we were able to show that if we could perfectly match the bandwidth of our, photons with the phase matching bandwidth, we could actually get 99% conversion. But the problem is our photons have a little greater bandwidth than our phase matching bandwidth. And so as a result, we lose a little bit of efficiency here, but we still do very, very well. And so what in these early experiments, we were up to 93% conversion efficiency. And so, of course, the question you ask, well, what's the added noise? You don't measure it, but can you measure high quality photons at the output if you put single photons at the input? So here I show, a measurement of a G2 measurement. And what you see here is the blue represents our input photons. And you see we have good quality input photons with a G2 that goes down to near zero. But you see that the idler photons, when fully converted, also have nice, good quantum single photon properties. So this was kind of early work done about 3 years ago, indicating that we could do not only highly efficient quantum frequency conversion, but we could also do it with very good fidelity and low noise. So then the next step, which everyone asks, well, okay, maybe that works pretty well, but that's only one characteristic. The more very important characteristic are these two photon correlations. You have a beam splitter here, so what you do is you bring two photons together. Do they exhibit two photon interference? And in fact, that's arguably maybe the most fundamental type of quantum interference, and one that's almost the most surprising. And this is what's called Hong-Ou-Mandel interference. And as I mentioned, I was at Rochester at the time when these experiments were being done. So when Len Mandel's group was doing a lot of it, and so Jeff Wu was leading this, and also with a postdoc Hong, we're doing this work. And this is one of the early measurements. And this is one of these results that seems completely surprising. And even to this day, even though I understand it, I can do all the math, I still can't believe it works. And it's this interference effect that works as follows. Imagine you have a beam splitter, and I have two identical photons here incident on this beam splitter. There's four possible outcomes. One is that this photon gets transmitted, this gets reflected, so that they both come out this arm. You might have this one transmitted, so you have one photon in each arm. You might have this one reflected and this reflected. Again, you might have one photon in each arm. And then you might have this one reflected, this one transmitted, so you have two photons in this arm. And so you'd think maybe there's a 50-50 chance that you have two photons, that there might be a 50-50 chance then that you have one and one. But it turns out that these two processes actually exhibit interference. And the end result is, when you go through all the math, is that these destructively interfere. And so the possible outcome from this measurement is that you can only get two photons here or two photons here. You never get one and one. And so that's measured in terms of looking for coincidence counts. If I put detectors here in this arm, and I have no delay between these two photons, there's a 0% probability of having a coincident count. And that's because both photons have either come out one arm or the other. It's, again, kind of remarkable that you get this effect. And it's, again, it's one of the real most fundamental aspects, but it's an indication of how good quality your beam splitter is and your photons. And so that's why people are always insistent that you do a Hong-Ou-Mandel interference when you're looking at novel sources of photons and building any type of photonic components. So I've told you that we have this frequency beam splitter here. And so what I want to indicate to you is that we can have exactly the same behavior, but in the frequency domain. So now imagine I have a blue photon and a red photon incident on my frequency beam splitter. So there's four possible outcomes. One is I can end up with two blue photons, maybe a red and a blue, another possibility of a red and a blue, or two red photons. But it turns out, due to quantum interference, I never get red and a blue. And so when you look at the outcome, these two cancel, and the only possibility is I have two blue photons or two red photons. I never get one of each. Again, it's kind of unbelievable that it works, but it does, and it works out just as you saw. And what's important to note about Hong-Ou-Mandel interference is that normally, at least how I was taught it, but now I realize what it is that you need identical photons at the output. You don't have to have identical photons at the input. So unlike the spatial case where they do have to be, it doesn't have to be that way. And here's an example where clearly these two photons are distinguishable, blue and red, but the clear part is when this gets converted to blue, they're indistinguishable at the output. And so Hong-Ou-Mandel interference is telling you about the output, not the input. So here we set up an experiment to observe this Hong-Ou-Mandel interference. And what we did is we used a microresonator here to generate correlated photons. And the microresonator allows us to generate correlated photons on a grid. That is, we generate photon pairs. We have the pump right in the middle, but now the photons are generated at modes of the microresonator such that every one here is generated along with another one here. Okay. And then we take those two correlated photons, let's say a red and a blue one, we mix them with a pump in our Bragg scattering four-wave mixing fiber. And of course, this spacing here is fixed by the microresonator. In our pumps, we can actually detune the pumps. We can make them identical to the spacing here, but we can also detune them if we so choose. And that allows us to see some interesting new physics. But what we'll see at the output, and the hope is that when the tuning here is such that this is equal to the frequency separation of our two generated photons. We should only get either two red photons or two blue photons coming out. So here's just reminding you about our microresonator. And this was actually early work we did a number of years ago. So interestingly, this paper has been cited a lot, but never published. And I don't want to go too much into the details, but it was one of these papers that for some reason could not find a home in a journal, and referees would not allow it to find a home in a journal, but it's still a highly cited paper on generating correlated photons, relatively narrow band photons, about 10 megahertz long. And so again, we're generating photon pairs here. They're on this grid. And so, you know, although this photon is not correlated with this one here has a direct correlation with this one when the pump is sitting right in the middle. And so here's just an example where we can generate photons that can be narrow band down to 30 megahertz using this technique. So these can be relatively narrow band. So here is our frequency converter. And this is an example where in this particular experiments, we actually had slightly improved the setup even more for the Bragg scattering forward mixing. So we're at 97% conversion. And this just gives you an idea of the conversion across, for photons as you detune them, across a certain frequency band. And you see we can maintain very high conversion efficiency up to almost 2 terahertz. And so here are the results. So when the pumps are detuned exactly by the spacing corresponding to the two photons, what we see then at that point, we're converting exactly between the two photons. And what you see is when the pumps aren't on, you get this kind of double exponential. This is like what you'd expect from a thermal source, as you might expect from generating photons in this four-wave mixing scheme. But when the pumps are turned on and you get frequency conversion, you can see here that you have basically no probability of generating coincidence counts in this point here. And you can see that we just get a flat curve. Now, as we detune the pumps, you can see you begin seeing oscillations here. And again, if you actually go through the math and you look at what expression you should see for this, this second order correlation, you get an expression that looks like this. That is, you have this double exponential, which again comes from the thermal nature of the photons. But then you have the sine squared, which corresponds to the pump waves being present. And so when delta omega exactly resonant equals 0, that's when you get the flat line for this coincident counts. And then as you now detune, the pump offset is not equal to the spacing of the two pumps, you begin getting what's equivalent to this quantum beating, which actually has been observed in atomic systems. It's exactly the same equations, same kind of math, same system, but it's quantum beating from two levels in an atomic system. This was observed by Gerhard Rempe's group. And you can see that we can, the solid lines represent the theory. And you can see as you increase the frequency here, you can see the beating gets more pronounced. And then, of course, if it gets really large, then you just get the double exponential again. But here again, you show very good agreement between theory and experiment. And we can see this Hong-Mandel interference in the frequency domain. So lastly, our next topic is on Ramsey interference. And so just to remind you, Ramsey interference can be observed under a number of different geometries, but it was originally observed, kind of in the atomic systems. And the idea was you had some two-state system, which consists of a ground state, excited state. You excite your atom with a pi/2 pulse. This is now putting in a superposition of the ground excited state. While it's in this superposition, the atom can undergo free induction decay, or maybe it undergoes regular decay, but then you hit it with another pi/2 pulse. Now, if nothing happened in the middle here, the atom would be in the excited state, and you could detect that. But if you have some kind of free induction decay, or you can change the phase of this interaction at this point here, at this intermediate point, what you find is that you can have something that now has this cosine sine dependence here. And so these are what are called Ramsey interference fringes. And so, for example, this might be just free induction decay, where the atom is just undergoing free induction decay here. And so depending on the time between these pi/2 pulses, if I change that time here, I end up measuring these fringes. This is well-known effect. It's used to give you a bunch of information, including the decay rate, because now if I have decay at this point here, what you'll see is the modulation of the fringes goes down. So we now have this frequency qubit, which looks like a two-state system. We have the frequency can be in the, a blue photon or a red photon, for example. That's our frequency qubit. And so by exciting a pulse, we can actually put it into a superposition of a ground and excited states, just like the atomic system. And so the idea is you could just have, put it in this superposition here and then propagate these fields. That would be giving it like a frequency dependent phase shift. And that would be like free induction decay. And then again, by hitting it with another pi over 2 pulse, at this point, oops, sorry, you can, you can determine, measure how much, what probability is that the photons are red or in the blue, and that should give you interference fringes as you change this phase here. So how did we do the experiment? Again, we have Bragg scattering forward mixing. We have 2 pump waves that come in and pump it. And then what we do is we take the signal idler after passing through and we just bounce it off a mirror. And as we change this distance here, that's changing the phase. That's telling you effectively like this free induction decay. And then we interact with the pumps going now backwards through the system. And then we detect if the photons are red or blue. And by doing that, you can actually see that for a weak coherent state, we can see these Ramsey fringes, but even for the case in which we put in a single photon, we can also detect Ramsey fringes here for this particular experiment. So lastly, I'll talk about something called frequency multiplexing, which is a way, it's a path we think that could be very promising in generating deterministic or near deterministic single photons. So again, as I showed you at the very beginning of the talk, one of the key aspects of building, for example, many photonic components, many photonic devices, including quantum computers, is to have, or ideally what you'd love to have is a deterministic single photon source. One where you just push a button, you send an electrical signal, and you get a photon right then and there. And certainly there are a lot of groups, at Calgary that are working on this, which is, using a number of different systems. And this could include, for example, you have quantum dots, which has been one of the big ones where a lot of advances have been made. And certainly a lot of work being done there. But as I mentioned earlier, we also can use parametric single photon sources. Now, one aspect of working with quantum dots and all these other systems is typically these have to be at cryogenic temperatures. And again, if you want to scale up to have 1,000 or 1,000,000 of these, that's really a challenge to have the whole system to be at cryogenic temperatures. So again, using parametric single photon sources, you can operate at room temperature. The problem is the probability of when a photon is actually, these pairs of photons is generated is probabilistic. And in fact, you'd say, well, just keep turning up the pump wave. But if you turn up the pump wave, then there's a probability that you might generate 2 photons, and that's not good. You always want just a single photon. And so, so the idea is, is there some way of taking this parametric process and making it more deterministic? And there is. One way of doing it is doing what's called multiplexing. So as I mentioned, you don't want to keep turning up the pump because then there's a probability of getting 2 photons. So that kind of limits you to the maximum heralding efficiency before you begin getting these 2 photon effects is about 25%. That is, if you turn out the pump, there's a 25% chance that a photon will be there. So what you do is just multiplex. Take a whole bunch of these single photon parametric sources and just wait. You have all these detectors here waiting for one of them to generate a photon. And then what you do is once one of them gets triggered, I know I have a single photon, and then I turn off all of them altogether. And so by doing some fast logic here and having a network, I can generate near deterministic photons by just having this kind of network of multiplexed photons. Okay. And so you can get to almost near deterministic, heralding at about 20 sources or in that ballpark. Okay. And integrated photonics really lends itself really well to that. And there have been certainly a number of approaches to do that. So there have been people putting it on a chip, people doing temporal multiplexing. Paul Kwiat's work group has done impressive work there. And then even combining the two, temporal and spatial. The problem is, as I'll mention in a second, is that to get to, let's say, 20 sources is very challenging, because in order to get into that regime, you have to scale up the system and the losses start killing you. And actually what you find is actually if you start above a certain point, it actually hurts to keep scaling up because the losses start getting really bad, deleterious for the photon generation process. So what we're going to do is to instead use frequency multiplexing. So the idea is that if we can herald all these photons, and these photons are generated here, let's say all these different frequencies. So let's say, we're generating them in a microresonator, for example. And so I'm heralding over them all these photons, but they're all at different frequencies. We don't know when they're coming out. But what we can do is once we see that we're generating a red one, we convert it to blue or aquamarine, I'll say here. If we generate a purple photon, we convert it to aquamarine. And so no matter what frequency it comes out at, we always generate it to the same frequency. And the beauty of doing this in the frequency domain is you just need to add more pump waves that allow you to do frequency conversion, but the system stays the same size. And so it does not scale with loss in the same way that temporal and spatial multiplexing scale. And here I show an example of this. So, depending on your geometry and how you're putting everything together, the spatial and temporal multiplexing, you can see you can get up to, with like typical losses that can be readily achieved. The best you can ever do is kind of 50% heralding. But you can see in our case where it doesn't scale with loss, you can get comparable to almost a low loss case. And by adding more sources, you can actually keep scaling and getting better and better. So this is the idea for trying to do frequency multiplexing. So sometimes it's easier to explain this when you look at the experiment. It usually doesn't work out that way, but here it does. So imagine this case here, where I have a Piplin device. In this particular case, ideally we want to make it a microresonator, but I'm generating correlated photon pairs. So some of the photons are going this way, and then the corresponding pair, the other member of the pair is going this way. So depending on what color this pair is, that determines the colors up here. So for example, if let's say the green one comes out here, it gets detected by this detector. I come in here, and let's say at this point, I don't want to change its frequency. I want to keep all my photons green. So I don't turn on any of the pump waves, Bragg scattering, forward mixing, and it just goes through the system. I generate a green photon. But if I generate an aquamarine photon here, which would be indicated by this detector going off, then what I'm going to do is turn on these two pump waves, this one here and this one here. It then goes through the system. I do Bragg scattering forward mixing, and I convert this aquamarine one to the green. Let's say this one is triggered. That means the blue photon came out. And so now I'm going to turn on, for example, this pump photon, this pump laser, and this pump laser. Oops. And so under those conditions, I'll convert the blue again to the green, so that no matter which photon comes out here, they always get converted to green. Okay, so this is the lookup table you can think of for that. And so we did that experiment, and sure enough, if we operate each one of these photons individually, you get kind of a typical heralding photon rate. But when you now do the multiplexing, you get an enhancement here of about 3.5 dB. It's not quite 5 dB, but it's still a significant improvement over what you might expect. And so this is indicating that we are getting multiplexing enhancement, and these are pretty good generation rates that we're seeing this here for these much higher generated multiplexing quality than you would from a single photon. And so here, for example, you can see in a particular case that the photons that are generated from the multiplexing process, depending on what the heralding rate is, but they're still pretty good here, even at the highest rates, where they're still at 0.06, but not too bad. But you can see if you go a little bit lower, you can get very good quality photons from this multiplex source. And again, in this particular case, I should say the coincidences, the accidentals, these are, basically you can improve this with our multiplexing setup. Okay, so you can improve it from what the single photon, channel version would be. So again, our scheme is that this could scale very nicely on a microresonator chip here. We could just take this particular microresonator, generating these correlated pairs, and then you just convert them, doing single, Bragg scattering forward mixing. You have multiple Bragg scattering forward mixing, so you always convert, no matter what photon comes out here, you always convert it to blue. And this type of scaling here could be produced very well on an integrated photonic circuit. So lastly, what I'm going to add is just one little aspect that maybe you didn't think about, which is the idea of using our quantum frequency converter for other applications. And one of them is for what's called temporal magnification. So imagine that you have some light field, and maybe this light field has features on it that are 100 femtoseconds in scale. Well, it would be impossible using a conventional detector to resolve these features. And certainly in the quantum domain, it would be impossible. So, if you take the fastest detectors in the quantum domain, about the best you can ever do, resolve photons, is of the order of tens of picoseconds. That's the best you can ever do. But let's say these photons were 100 femtoseconds apart, you could not determine that. But imagine we had some device, which I'm calling a temporal magnifier, which can actually take these features and expand them and preserve all the fidelity. That is, that now our new device, new temporal waveform looks something like this. In this case, we're magnifying it by a factor of 1,000. So that, now it's 100 picoseconds. Well, now our relatively slow detector could be resolved. And so, we've done a lot of work on this in the classical domain, but now we're trying to do this in the quantum domain. And again, for quantum applications, you need to do this with 100% conversion efficiency and no added noise. So that's a key part. So how can we do this? Well, it turns out you can use this concept called time-space duality. It was first actually conceived by Brian Kolner, but certainly if you want to read a review paper on this, there was the one that we wrote a few years ago on this, but discussing all the interesting applications. And there's a lot of interesting things you can do with this. And the way it works is as follows. It's based on space-time duality. What does that mean? Well, if I look at ordinary diffraction of a field, it obeys this Fresnel equation, which probably many of you are familiar with. It's just, you have a second order derivative in space. This corresponds to diffraction here. And this is just Fresnel diffraction. And you can think of it as that this lens here, if I have a wavefront comes in, the lens just applies a quadratic phase shift. That is, it's basically just curves the wavefront. So it applies this quadratic phase shift, and that's what creates the focus. And it turns out you can solve that using Fresnel, equations. Of course, we never do this because it's a lot easier to just use the ray picture, and we never think in the wave domain when we think about focusing with a lens, but that's how it works. Well, it turns out that if you look at the equation for the evolution of a pulse in a dispersive medium, it obeys the same kind of equation where beta 2 here is the group velocity dispersion. So that's actually kind of interesting here. This says that the equation describing the propagation of a pulse in a dispersive medium is the same, it's identical to Fresnel diffraction. So everything that you observe in the time domain here everything observed in the spatial domain here can be observed in the time domain here. And so this is what's called space-time duality. It's based on the fact that the equations describing dispersive propagation and diffraction are isomorphic. And so as a result, if you can build a time lens, which all you need is something that provides a quadratic phase shift, then you can do imaging in the time domain. And so that's where we get this temporal magnifier. And so how do we do that? Well, we do our same Bragg scattering four-wave mixing, but now for one of the pumps, we apply a linear frequency chirp. And if you think about a linear frequency chirp, that corresponds to a quadratic phase shift. Linear frequency chirp, quadratic phase shift. So by just chirping one of the pump waves and just applying a linear frequency chirp, I can produce a time lens here. And so now when this pump that's been chirped interacts with the signal, the idler will look just like the signal, but as if it has passed through a lens. And then you just do ordinary imaging. So just like I said here, you have a time lens here, and then you just do dispersive propagation. So here in the regular lens, I apply a quadratic phase shift, and then I just do ordinary propagation. So our time lens can do exactly the same as ordinary propagation. And so that's the imaging that we're doing in this system. And so what we do is we take superconducting nanowire detectors to time resolve our signal. And in this particular case, what we do is we take a signal that has just on average 1 photon in it, and we actually put a dispersive delay, we put a delay into it, and we kind of split it into 2. And so this allows us to do the following experiment. So we take our pulse, which consists of about a photon on average, and then we pass it through a dispersive element. We pass through polarization maintaining fiber, because now we have 2 polarization components to our photons. They get split because of the birefringence here. And so it turns out that in our particular case, The two pulses that come out are about two picoseconds apart. But now we pass it through our time lens, and even with our relatively slow photoconductive, superconductive detectors, we can actually resolve them, because now these two photons have been split into 390 picoseconds apart. So we can actually resolve it. So there's a lot of interesting things that could be done with this system, but certainly we can now measure correlations, quantum correlations that are certainly sub-picosecond. We're in that ballpark. So the future, so we're working on a number of things. One is to further improve our frequency multiplexing with single photon sources. I just want to point out that in the frequency domain, you can have very complex unitary interactions. And so just to show an example here, is you can do the equivalent of boson sampling, but in the frequency domain. So normally when we think about boson sampling, you have all these beam splitters that cascaded, but we can do the same by just adding different pump fields here. And so by adding more pump fields, we can get that. So imagine, for example, that you have, let's say, 12 modes that can all interact here. And now in propagating through the material, and again, the length doesn't change, this is fixed here, we can get interactions between all these 12 modes. And again, we could scale it up to 24 modes, 48 modes. The length doesn't scale, and the losses don't scale with size as they normally might with boson sampling, where you have this. And so these type of multi-mode unitary interactions could occur actually in the frequency domain. And in a way, they can overcome losses that are not so easily or readily done with ordinary boson sampling. And lastly, currently experiments we're working on is doing temporal processing mode sorting. That's based on this temporal magnifier technology, and hopefully you'll be hearing about that in a few months. So thanks for your attention. I just want to acknowledge a great group of students and postdocs that have done all these work, in particular Chaitali Yoshi, who really led a lot of the works over the last few years. She was a fantastic student. She's currently now doing a postdoc at Caltech. She's gone over to the dark side, away from photonics. She's working with superconducting qubits in Mohammed Mirhaseni's group down there. So thanks for your attention.
Thank you, Dr. Gaeta. So now Dr. Gaeta would be taking questions. So you can unmute yourself and ask him, or you could type it in the chat and I will ask him the question.
I think my dog had a few questions. I just heard about it.
Okay, so the first question is from Kim. When you use four-wave mixing to generate heralded single photons, what is the characteristic of the source? Is it still a Poissonian source that is limited to low pump powers if you want to keep your photon statistics low?
So, I mean, the pump source, I'll just say right now, I think for the most part, the statistics for our classical pump do not enter in, at least to first order, in the statistics of the signal neither photons that are generated. And so, so I would say that the photons that are generated, their properties, if you look at one at a time without looking at correlations, would look just like that of a thermal source. And that's because it's behaving like an amplifier. So if you took, it really has all the properties of a regular amplifier. So if you took, for example, even an amplifier operating by stimulated emission, and you look at its statistics, those photons coming out look thermal in nature. And it's exactly the same here. But of course, when you look at the pairs, the correlations, that's when all of a sudden, and then I detect one. Well, now I can now change from what was apparently a thermal source, but of course I'm manipulating my pump, and I can change it into this Fock state. I don't know if that answers your question. But.
Yeah, it does. You just said something about turning the thermal source into a Fock state. How exactly, sorry?
So what I would say, and this was, kind of the first observation, but, normally if you look at thermal statistics and you look at just the pump photons individually, and now you're doing a measurement. and you measure the statistics, and it'll behave like a thermal source. But now when you do the heralding, is at least for the short period of time, the time window that you've opened up. So you do a detection. So let's say you do the following experiment. I'm waiting for a photon. All of a sudden, I detect a signal photon. I've heralded that. And what I do is I turn off my pump photon. I turn off my pump wave. And so now there was only one photon generated. And so by doing that, I have a Fock state. Of course, I can keep repeating that measurement.